All right, friends, here we go. So today we are going to talk about, we're going to start into the second part of calculus, the admittedly fun part, the rocket science part, which is called integral calculus. We're going to do things called a process called integration, which leads to a whole bunch of different cool things we can do with math. And arguably, a lot of people would say that that is the body of calculus is in integral calculus. What we've been doing is the derivative side, so we call that differential calculus. So weirdly, the book gets really weird right in here, so things are going to be a little out of order. I'm trying to make better sense of it for you. So this is actually in chapter 4. It's the technique we have to learn to do integration. So first of all, they toss that in there without any context. So let me put that in context so we can understand what we're doing. So we need to do a process called integration. And in doing that, sorry, we're going to find this, this integral sign, which is just an old school script S, which you're also going to see us using the capital Greek letter sigma because we're adding things together. This is just a variation of that. So when you see this, that means we're going to integrate something. So we call this the integral sign. Sorry, I don't know, my throat's all scratchy today. Anyway, what we're going to do is we're going to see this and notice that this sign doesn't have any numbers around it. In a little bit, we're going to actually put a number down here and a number up here. It could be a number, it could be other things, but you're going to see something at the bottom of this S, the script S. And you're going to see something at the top. Right now, you don't see anything. So this is super, super important. When you do not see anything here, we call this an indefinite integral, meaning the answer that you get is just kind of a general answer. It's telling you just kind of a meta answer, kind of a big picture answer. If you see things here, right here or right up here, that's called a definite integral, and the answer is going to be a specific answer. So right off the bat, I'm going to tell you, when we do indefinite integrals, you need to add this plus big capital C at the end of every single answer. When I say every single answer, I literally mean every single answer, because this plus C indicates to you that it's that meta answer or that big picture answer, if you want to think of it that way. If you don't have that, then your answer is specific, and that's the answer for a definite integral problem. So let me be uber clear here. If you are given this as a question, you're going to integrate something, and you don't put the plus C, the answer is completely wrong. I'm just saying that right now. If, on the other hand, you get a definite integral and you do put a plus C, it is also completely wrong. It's like you're saying, hey, well, how many bones are in the body? And your answer is chocolate, right? The answer and the question have nothing to do with each other. So please make sure you're very clear on that. And is that going to cause a couple of you some grief? Yes, it is. But unfortunately, for some of you, grief is the only way to learn. And so you will learn very quickly that the indefinite integral needs the plus C, has to have the plus C. So let's talk about what do we do when we see this sign? Well, it's not complicated. You've been doing differentiation. You've been doing derivatives, right? And you know how to do that really well. It's pretty straightforward. All this is going backwards. And so the textbook calls it anti-differentiation. I like to make it a little clearer and call it reverse differentiation. And here's the beauty, my friends, is as you're starting out, you can always check your work. When you get the answer to an integral, just take the derivative, and that'll be the question. It loops back around. Let me give you an example. So, for example, let's say that I have here a function, f of x equals 3x squared, and I said, hey, would you please take the derivative of that? You know exactly what to do. You bring the 2 down here and multiply, so I get 6x, and reduce this to a 1. Well, integration is, well, how do you go backwards? You're literally going to reverse the process. So what are the steps you did? Well, I multiplied by whatever this was. So instead of multiplying, you're going to divide. And I subtracted 1. Instead of subtracting 1, you're going to add 1. It literally is just like that. So there's not really like a new thing to learn here. It's just you're going the other direction. It's like when you were young and your teachers taught you addition first, and then you learn subtraction, and that's just backwards addition. Or you learn multiplication, and then they taught you division. Oh, it's just backwards multiplication. Same thing, the same exact process. It'll take you a second to get used to it, but the idea is you can check your work as you're starting. So you can double check that you got it right. And it shouldn't be too much difficulty. So let me just be really clear right here. If you could tattoo this on your arm, that'd be great. So the idea is that the integral of a derivative takes you back to the original function. So like the ln and the e, e to the ln, how those cancel each other, right? It's the same thing. The integral and a derivative, they cancel each other. So the integral of a derivative of a function is equal to the function. But in this case, this is an indefinite integral, so notice I have to put the plus c. And I'm going to show you why that is in just a moment, my friends. So look here. I'm actually going to show you right now. So look at these. Oh, why is there a spider on my... Get out of here, spider. I have a spider friend here with me. So look at these three different functions. I have f of x equals x plus 2, f of x equals x minus 3, f of x equals x. Three completely different functions. But when you take the derivative of each of these, notice how the derivatives are identical. Right? The derivatives are the same, meaning the slope of these is the same. What the derivative answered was, hey, what is the slope at a point of a function? What the integral is answering is what function came from that slope, what potential functions come from that. So when you integrate this c is accounting for all possible answers here, which you can imagine are literally an infinite number of them. Plus 2, plus 3, plus 4, plus 1.5, plus pi, plus e, plus whatever. All of those are contained in this answer. Okay? So in this case, when I integrate 1, when I go backwards, so if you do the indefinite integral of 1, the answer is x. And oh, how did you do that? Well, wait a second. What's the derivative of x? 1, right? It's just backwards. This is wrong, because do you see this answer anywhere except for here? I don't. So I have to add the plus c to account for this answer and to account for that answer. Do you see what I'm saying? If I just take this answer, I can't get here. I can't get there. I can only get this one, which is not correct. The integral, the answer is all of them. All of these. X plus or minus any number is the answer, which is accounted for there. And for my people who are fussy, remember that the reason we put plus c is because c can be any number, positive or negative. All right, let's move on. So let's look at the rules here. And I made a mistake here. I put c here. I should not have done that. We should have called this some other number like an n or something. I'm just going to write n here. An n. So if you have the integral, so here's just the integration rule. So if you have the integral of a number, the answer is just that number times x plus c, which makes sense because what's the derivative of nx? Well, n, right? And so then the rule for the power rule for integration is we add 1 to the numerator. Excuse me, to the exponent. We add 1 to the exponent. So whatever n was, we add 1 to it, and then divide by that number. And if this is a fraction, if this is a decimal, doesn't matter. Just bring it down. Just bring it down. Same thing here. We know what the derivative of the ln is, right? So if I integrate 1 over x, or dx over x, or when we get to the chain rule, du over u, I get the ln of the absolute value of u. We have to put the absolute value brackets here because remember, we can't take the ln of a negative number. And our good friend e to the x, just like we said, what's the derivative of e to the x? The answer is e to the x. What's the integral of e to the x? The answer is e to the x, of course, but we have to add the plus c. So nothing really new there, just backwards. We have all of our trig friends here. Again, they're just backwards. Integral of the cosine is the sine. Integral of the sine is the negative cosine. Integral of the secant squared is the tangent. Integral of the negative cosecant squared is negative cotangent. Integral of the secant tangent is secant squared. Integral of cosecant cotangent is negative cosecant squared. And then we have our arc sine, tangent, secant things. There's the other ones are here. We're going to need this later in Calc 3. This is gonna come back and visit us. And I don't necessarily want you to memorize it. I know that might be heresy for me to say we don't have to memorize this, but we use this so infrequently that I just want you, I tell everybody this every time I teach this, is that I really just want you to recognize these, that when you see something that's 1 over something like this, or just you see it, that just has to ring a bell. Oh, I think there's a rule for that, and you can look the rule up in the back of your textbook. There's integral tables. That would be, what I don't want is for you to see this. Well, I can't do that. Well, hang on, you can. You just got to find it. Is what we're doing here. So. Super easy to check our answers. Super easy to check. So here's 4.51. So we have the integral of x plus e to the x, and we always add this dx. I'll explain why later, much later, not right now. Just that has to be there, and you'll see that when we get to substitution, which is the chain rule for integrals. We have to have a du there, but don't worry about that right now. Just I want you to get in the habit of putting it there. That the integral of x is x squared over 2. Well, how did we get that? Well, wait a second. What's the derivative of x squared over 2? Bring the 2 down. Well, that 2 cancels this 2, and subtract 1 is x. What's the integral of e to the x? Well, the integral of e to the x is e to the x, and then we add the plus c. So you can check these. Just take the derivative of each of these. If I just gave this to you before and said, what's the derivative of this? This would be your answer, which is right there. So you got it right. Yeah. Really, the only thing you're going to get wrong is the plus c part. Let's look at a couple more here, my friends. Here's 4.52. So here's a whole long thing here. This looks like this is just all the power rule. So, so we look at each of these. We integrate each of these separately. No worries. So I've got 5x cubed, so I'm going to raise this cube to a 4th and then divide by 4. Whatever is here just stays. So 5x cubed becomes 5x to the 4th over 4 minus 7x squared becomes 7x cubed over 3. 3x, remember when we have just a single variable to a power, there's a 1 there really. So then 3x becomes 3x squared over 2. And 4, remember that the first rule I said was if you just have a number, it's just the number times x. But remember, this is really x to the 0 power. So if you want to think of it that way. So then this becomes 4x to the 1st over 1, right? We don't write that, but that's where that rule comes from. It's just a variation of the power rule. And the ubiquitous plus c, the required and ubiquitous plus c. Here's another one. X squared plus 4 times the cube root of x over x. The book goes crazy very quickly on these. So here we say, well, we don't know the quotient rule version of this yet. So can we fix this algebraically? And the answer is yes. I can break this into 2 separate fractions. Well, isn't x squared over x just x? And isn't 4x to the 1/3 power divided by x, 4x to the negative 2/3 power? The answer is yes. So that's just some algebra. Now, once you get here, this is actually very similar, right? So what's the integral of x? Well, x squared over 2. And what's the derivative of 4x to the negative 2/3 x? Well, to the negative 2/3 power, sorry. Well, again, we don't care that there's a fraction. We're literally going to add the number 1. So negative 2/3 plus 1/3, plus 1 becomes 1/3. And then don't get fancy on me. Just take whatever you get here and just move it down in the denominator. And you can leave it there. We don't have to simplify. So 4x to the negative 2/3 becomes 4x to the positive 1/3 divided by 1/3 and our plus c. The book skips really quickly ahead to initial value problems. There's a whole thing we're going to study later. There's classes in math you can take on this later on. After calculus, you would take something called differential equations. There's two kinds. There's partial differential equations and ordinary differential equations. Super fun and not difficult once you get to Calc 3. Those are very simple. This is actually a differential equation problem. I don't know why they're putting it here, but I'm just going to show it to you now. So these are called initial value problems, and this is where you are taking the integral of something and trying to find the specific equation or the specific function that it came from. So in this case, we have an initial value, that's why this is called here. So whatever the function y is, y at 0 is 5. And I just want to point out that when they write it like this is the same as saying f at 0 is 5. So whatever the value, this is our x value, right? This is the x value here, the input, and then the output at 0 is 5. Okay. So then the equation is dy dx is sine x. Now, I'm jumping right ahead to differential equations. What we do is we literally treat this dy dx as a fraction. So I'm going to multiply both sides by dx to get it to look like this. So, and the reason we do this, I'm skipping way ahead, is so that the variables are all matched up. So notice I have x's and dx's on one side and a dy on the other. So literally what we're going to do is we're going to integrate both sides. And so the integral of dy becomes y, and the integral of sine x dx is negative cosine x. And I put the plus c. Now, some of you will say, hey, isn't there a plus c on this side too? And the answer is yes, there is. There's a plus c here and a plus c there, but because plus c can be any number I want, I can literally combine those two c's to make it one c. Oh, coyote's in the backyard there looking around. So this c accounts for both. And remember that c accounts for both sides. It accounts for negatives and positives. So we can just leave it as a c. So here is our equation right here that we came from. We're going to now substitute these values in here. So I'm going to substitute 0 in here for, sorry, I made a little error there. So we're going to substitute 0 in for cosine because that was the x value, right? And 5 is the y. So I have 5 equals negative cosine of 0 plus c, because we're trying to find what c is for this particular case. Well, cosine of 0 is 1, and negative that is negative 1. So I have 5 equals negative 1 plus c. Add 1 to both sides, and I get c is 6. So y equals negative cosine x plus 6 is this, will generate this value from this differential equation. Okay. Don't worry too much about this now because we're going to do much more of this later. So this is just, like I said, the book is kind of all over the place here. Here is a physics version of this, same thing that we just did here. I'm going to go through this, but this is this is a little bit of fire hosey for you right now, but I'm going to walk you through it. So in physics, what we can do is we can take acceleration and velocity and integrate those. So in this case, I have an object that is moving at 88 feet per second. That's its velocity. And it has an acceleration of negative 15 feet per second squared. So then we say at time 0, so our independent variable here is time when we're doing physics, right? So at time 0, I'm starting at 88 feet per second. We're slowing down, right? So negative acceleration means we're slowing down. And so then the question is, when is this thing going to stop? When does this stop? So what we do is we take this knowledge that we already know, that acceleration is the derivative of the velocity. We take that knowledge, and we're going to say that we have an initial velocity of 88, but we're slowing down, so that we need to come up with a new function to talk about how to put the acceleration and the velocity in the same function. So we're going to start here with this and say the derivative of the velocity is negative 15. So I'm going to integrate this, right? I'm going to integrate this function. And when I integrate the derivative of velocity, don't I get velocity? The answer is yes, you do. And so then that velocity becomes negative 15t, right? Because what's the integral of negative 15? Negative 15t. And we add that plus c. So then we say, well, wait a second. We know what this plus c is. That plus c is actually 88 because when time is 0, this term becomes 0, because we know it was our initial velocity was 88. So at the velocity at 0 has to equal 88. So negative 15 times 0 is 0, so that means c is 88. So then our velocity equation is negative 15t plus 88. We then set that equal to 0 because the question was when does it stop, meaning when is the velocity 0? And so then we do our algebra, and we get at 88 15ths seconds. That's when the object stops. Okay?